Boom. Hello and welcome back to Calculus 1, section 3.3. We are talking about easy way to take the derivative. So this entire section is dedicated to teach you shortcuts. And if you find this something that you don't like, your alternative is to take the limit every time. So this section is meant to make your life easy. The same way how you, it's pretty much the same deal like when you learned and memorized multiplication table. Instead of going 3 plus 3 is 6, plus 3 is 9, plus 3 is 12, plus 3 is 15, you say 3 times 5 is 15. There's no calculation 3 times 5 is 15. You memorize that. So when you see 3 plus 3 plus 3 plus 3 plus 3, you know it's 3 times 5, which is 15. You memorize the multiplication table. This section will outline the rules that you memorize so you don't have to do the limit h goes to 0, f of x plus h minus f of x over h, and then spend whatever amount of time to compute that. So just to remind you that the derivative of a function was defined as the limit of the difference quotient, which I just mentioned, and the limit of the difference quotient. And if you have to take the limit using this, let's say f of x is given as 2x squared minus 5, you would first create the f of x plus h piece, which is 2x plus h squared minus 5, which is 2x squared plus 4xh plus h squared minus 5, and then you plug all of that into the formula to get the limit, which gives you eventually the derivative. So that's going to be 2x squared plus 4xh plus h squared minus 5 minus 2x squared plus 5 when you apply the negative sign over h. So 5 dies and 2x dies, and you can factor out h to leave the 4x plus h over h. These guys cancel, and when h is 0, you just get 4x as the answer. So the derivative is just 4x. Now we learn the rule in this particular section, which will get you from here to here in one step because you memorized the rule. That's what we are learning today. We are learning how to bypass the entire calculation you see here, and we are going to dedicate the rest of this chapter to learning rules and shortcuts so that we don't have to bother with the limit. The first rule that we are, I would say, real learning is the one from last class where I said that the derivative of a constant is 0 because there's no change. If the function is constant, it's not changing, therefore the derivative, which measures the change, must be 0. So the notation now is going to be a little bit different, and what you see here is this d dx. That thing is called the differential operator, and that is like the instruction on what to do. Whatever you want to take the derivative of goes into these brackets, and then obviously the answer goes on the other side. So this over here is called the differential operator. The function goes inside. This happened to be a constant, but you can have x squared in there. And this would be the answer, which is the derivative. What this statement technically says is, look at the board, take the derivative of constant to get 0. So this d dx is an instruction. Well, we are going to dissect that further and get more meaning out of that statement. But for right now, we are learning how to properly read it and understand it. So it's the instruction. You know instructions. License and registration. That's instruction, right? You know what to do. So over here, this is the operator which says take the derivative of whatever is in brackets. We're going to have integral down the line, the squiggly line, which will say integrate whatever is in there. So now this operator, in calculus, you learned those three operators. You learn the limit, and then you have something in here. You learn the derivative, dx, and you have something in there, and you learn the integral, and you will have something. I know it's invisible ink, but they all work the same way. You have these operators you can think of them as mathematical operations that are applied to functions. They change functions, where you have addition, subtraction, and other mathematical operations that deal with numbers and variables. So now if you are looking at the derivative, this is your first rule that you looked at. The derivative of a constant is 0. And now I ask you, what is the derivative of number 5? And your answer is, what is the derivative of pi? Right? So it's a very simple rule. And if you use common sense, right, while memorizing this, you will know that the derivative of a constant is 0 because derivative measures change. There's no change in a constant, so it should be common sense. The next rule which you are memorizing is the rule that will take care of the polynomial terms, and then also anything that has x to an exponent, whether it's positive, negative, fraction, whatever. So the derivative of x to the n is n x to the n minus 1. You are memorizing this, so you don't have to do the problem using the limit like I did up there. So now, what is the derivative of x cubed? (3x squared). Because if you carefully observe, the exponent is n, which is 3, so you copy the 3 in an n spot, and then 3 minus 1 is 2 for the exponent. What else falls into this category? Definitely the derivative of square root of x. How would you solve this one? 1/2. Very good. So you will first rewrite this as x to the 1/2, and then you will hit it with a rule. Show you what?
So you get the x comes out of. Then how
So now, what is the derivative of this? Very good. Which you can write as 1 over 2 root x. So some people just memorize because it's a very, very frequent derivative, that the derivative of root x is this. But you see that you're actually using the rule above to solve the problem because it's just minus 1, right? So in this particular problem, we rewrite the problem first to put it in a form where it's easy to use our rules, and then we move along with the problem. So what is the derivative of third root of x to the 5? Try that one. The first order of business is obviously to rewrite. So what should I write? X to the 5/3. Very good. So knowledge of basic algebra is extremely important, and that's what you have. And now you apply the formula. So what should I write? 5/3. X to the 2/3. Very good. Because you are subtracting 1. 1 is 3/3, so 5 minus 3 is 2. Good. Good. One more problem. What is the derivative of 1 over x to the 9th power? We first rewrite, right? Very good. We rewrite as x to the negative 9, and then negative 9, x to the negative 10, and then we write it nicely, right? Because we don't like negative exponents on x, so we write it as a positive exponent, which pushes it in the denominator. And then we have rules that help us work on a bit more complicated cases. What happens if I multiply constant times x cubed? So let's say if I have to take the derivative of 5x cubed, how do I deal with that? So we first learned a rule called the constant multiple rule. Constant multiple was not on the test. That's.
Well, no, it was like just like you had to take the number and take it out.
Oh yeah, the rules for limits. Yeah. Well, that's why it's possible to do in derivatives as well, because it is one of the basic properties of limits, and because the derivative is defined through a limit, it propagates through.
Okay.
So constant multiple says that the derivative of c times some kind of a function, you can keep constant in front of differentiation and then just worry about differentiating a function. It's a really cool rule. This rule is one of those rules that will just be automatic for you after doing 10 examples, because it's everywhere. This is you're constantly doing this. So I'm going to write out a problem at first, but then you will see later that you will be skipping all of this stuff. So 3x to the 5. By this rule, I can kick 3 outside and just take the derivative of x to the 5, which is 3 times 5x to the 4th, which eventually gives me 15x to the 4th. Now, what you are going to do in the future is you will probably just say, oh yeah, 5 times 3 right away, you know, skipping all of these steps in this work. But again, as I said, this takes time. So what is the derivative of 2 square root of x? So what is the first step?
Kicking out the constant.
Kick out the constant, yes. And then, didn't we solve already the derivative of root x? So we just have this case 1 over root x.
First I put 2x over 1 over 3, that's wrong, I guess, in a way.
2x over...
Like, 2x and then 1 to the 2.
And this is the derivative that most of the time triggers me when you do something really crazy for it, because it's this simple. But let's see. So what do you have for 8 divided by x to the 3? What should I do first? So kick out 8 and rewrite the rest of the problem as x to the minus 3, right? Then we have 8, negative 3, x to the negative 4. And then we put everything together as negative 24 over x to the positive 4. So the next one is the sum and difference rule. They only call it a sum rule, but it's a sum and difference because both addition and subtraction works the same. Its derivative of two functions that are subtracted can be done as two separate derivatives. So if you have the derivative of f of x plus or minus g of x, that means that you can do the derivatives separately. So this means that you can deal with a problem like this: x cubed minus square root of x in one shot. This formula technically tells you that every term is independent from the other term when you're taking the derivative. So you take the derivative of f of x independently from g of x. This rule doesn't work for multiplication, but it does work for addition and subtraction, which is good. So what's the derivative of x cubed? And how about the square root? Very good. The spicier version would be for you to consider, let's say, 5x squared minus 3x plus 8, the derivative of that. What should I write? Ten x minus 3. Are you all agreeing on this? I would like to take one problem from the homework. This is about half of the lesson so far. So here's one from the homework. It says this is problem 24. Find the derivative in respect to t now, because the variables are all t's. 4 root t plus 1/4 t to the 4th plus t plus 1. how do we do it with the first term? What should I write?
You write it as 4t to the
Okay. So we have the first term, we need to rewrite as 4t to the 1/2, and then all the other terms stay the same. Okay, we can simplify that. Good. And now what? What is the derivative?
You got 1 over root 2x and 1 over 2 times root x.
1 over 2?
1 over 2 root x.
It's 2 over. Right? Yeah, it's time. So it's 2 over root t. And then what happens to the next one? T to the third, good, because 4 will cancel a quarter. And then what happens next one? And plus next one? 0. Good. There we go. Now maybe if you practice this enough, you will get there sooner than later. For a term like this, you say, oh, I copy the 4, and as a block, I know that the other thing is this. So they cancel, and you get 2 over root t. You know, you have to kind of learn to see these things in blocks. So you know what the entire portion of the problem looks like. You know that you're supposed to copy the 4, and then you will just multiply it with whatever this thing is. The same thing like here, 4 drops down in front to multiply 4 a quarter, and that 4 cancel out. So we have no constant in front, this one. And then just 4 minus 2, or 1, 4 minus 1 is 3. And you have plus 1, and then 0. So it just, you know, it will take time for this to sink in, but if you see these blocks of how they because the whole idea of 3.3 is to learn shortcuts, so you don't have to go through that long limit. All of this can be done using the limit. So that was from homework. The next one is the exponential function. First of all, what's the derivative of e? What's the derivative of e? Is 0. E is a number, derivative of a number, derivative of a constant is 0. So the derivative of e to the x is e to the x. This is the only function that returns itself as a derivative. No other function will do this.
It has to be e to the x, not c to the x.
E, yeah. Has to be special base e. Now, there is a little bit more powerful version here, which involves like e to the 3x or e to the 10x, right? Or e to the negative x with this a, which drops in front. So now you're memorizing it for a short period of time, because later on, I think 3.6 is when we do the chain rule, and this a would be just be natural thing for you to drop it down like that. So my quick question, well, 2 questions for you is what is the derivative of e to the 5x? 5e to the 5x, good. And what is the derivative of 7e to the negative x? Nice. Good. All right, so you guys are getting this. And I'm going to actually box this formula here, because that's the main formula. The second one you are actually going to relearn through chain rule. Sense the tone. tangent line. The most important problem of chapters 3 and 4 is the tangent line problem. Derivative measures the change, slope of the tangent line measures the change because that's what the derivative gives. So figuring out tangent line is the central problem of Calculus 1. And then integration is the heart of Calculus 2. And then Calc 3 is the repeat of Calc 1 and 2 in 3D. So the central problem that we are focusing our efforts to is the tangent line problem. Find the tangent line for function blah blah at the point blah blah, right? So you have to find the slope of the tangent line through the derivative, and then you have to use the algebra to find the equation of the line, which is the tangent line. So earlier we used limit to find the slope of the tangent line. Right now we have the derivative, so it's going to be much faster and much easier. We don't have to grind through infinite algebra of limits. So find the equation of the tangent line at x equals 3 for the function f of x equals negative 2x squared plus x minus 1. We learned that the derivative computed at the value, in this case 3, is the slope of the tangent line at that point. So if I am to find the derivative, which you will tell me what it is, anyone? Negative 4x plus 1 is correct. This is the derivative. And here is the big notation, intensive, I guess, line that says slope of the tangent line is equal to the derivative computed at the point A. So we are looking at the derivative computed at 3, which is going to be negative 4 times 3 plus 1 gives us negative 11. So we know that the slope is 11. So this is why those derivatives, this whole section is so great. We don't have to crank the long limit. All we need to do is to simply take the derivative and then plug in 3. Negative 4 times 3 is negative 12 plus 1 is negative 11. Yes?
Why 11 and not negative 11?
It is negative 11.
Yeah, you wrote 11 up there, and then m equals below that, you wrote 11.
Oh, it is negative 11. See? You just,
Oh, there it is.
yeah, see? It's clearly negative 11. Yeah, I do that all the time, so good thing that you guys are paying attention, otherwise it will be,
He's so
yeah, I know. I mean, someone has to pay attention.
my brain is literally
Yeah.
just math.
So yes, negative 11. So the slope is negative 11. But please note this. This is the most important part here. Slope of the tangent line is the derivative computed at the point. Which point? The point that it's given to us. So the slope of the tangent line is the derivative computed at the point of interest. In this case, yes. Could be anything else. So what do I have so far? I only have m is equal to negative 11 and x is equal to 3. I need y. Well, we know that y is f of x, so f of 3, so plug 3 in the original equation. That's 9, negative 18, negative 15, and negative 16, I hope.
Yeah.
Sounds good? So now we can go with y equal mx plus b, and we have y, which is negative 16. We have m, which is negative 11, times 3 plus b. So that's going to be negative 16 plus 33 is equal to b. B is equal to what? Very good. So what's the equation of tangent line? Y equals negative 11x plus 17. There it is. Now, this tangent line here is the tangent line at 3. If you move anywhere else on the same function, it's going to change, right? Because remember, we used 3 to calculate slope, to calculate y value, right? We used 3 to calculate everything we need to come up with that line. If you use the same function and you use number 4, slope changes, y value changes, and that changes the entire tangent line. So you are guaranteed only one thing. Tangent line is a linear line, right? Y equal mx plus b. That's what it is. But you have to compute the entire tangent line from scratch every time, because depending on the function, that's the derivative, and then depending on the point that you're looking at. Remember that I said in class that the derivative is the function that you get which can generate all possible slopes. So I will tell you that the derivative of this function was, negative 4x plus 1. That's the derivative of the function. And now I'm waiting for input from you to tell me at which point I'm going to measure the change. Now, what is this equivalent to? This is equivalent to you measuring the change in population in time, you measuring a velocity, you measuring, something that is changing in time. Every time you push on the gas pedal, we'll talk about this in the class, every time you push the gas pedal, the velocity changes. The acceleration is the first derivative of velocity. So when you push the gas pedal, velocity changes. If you push the brake, that's also acceleration, just a negative one. The velocity decreases. What is the velocity? Velocity is the change of distance in time. So you will see, we'll have a separate lecture on this whole thing, and you will understand how the motion actually works through this. So we now need to learn the mechanics of taking the derivative so that we can apply it, and then you can go on with your engineering and whatever your disciplines are, which require calculus, which is business, which is medical field, which is technically everything else. The last part of this, actually, you know what, before we jump into the last part, which is higher order derivatives, let's take a look at one more tangent line problem. So find the tangent line. That's this TL question mark, means find the equation of the tangent line. And let's say that the function f of x is 3 over square root of x minus 4x at x equals to 4. So let's see what you get. Do the entire procedure, the derivative, everything else.
1.1 be 1?
Yes.
Really?
Yeah.
Yeah, that way I'm not just guessing on it. I can actually sit down and look at it.
Yeah. It's very easy. I just click and that's it.
So that like the first thing is gonna happen?
Yeah.
That's great.
Not the
It's-
geek came out, but when's the next homework that I open up?
6 a.m. tomorrow, but it could open earlier if you guys want to practice it tonight. It's perfect.
I don't.
Yeah, open up the
Yeah, open up and make it.
For tonight?
Yeah.
Deal.
So then tomorrow 3.1 will be good? For sure?
No, we'll toss it in with the rest for the weekend sometime.
Oh, alright, cool.
It's easy. I have divine powers. You don't understand what my powers are.
I just
I
feel
can
like
make
that's
things happen like this. That's you know.
The whole section, the whole class of homework due tomorrow, right? You can do that?
I can make the whole thing be due tonight or in a week. Like I can open everything chapter 5 due tonight at midnight.
I'm like brain dead.
I can also make it to be due at 11:37 if you want to. It's like I know. You just don't understand. All right, so let's take a look at this. We have the first order of business would be to rewrite the function so that it's easy for us to take the derivative. And now I start the separate line for the derivative. So the first line is for the function. The second line says derivative is. Copy 3, then we have negative 1/2, and then it's going to be x to the negative 3/2, and then minus 4. Because negative 1/2 minus 1 is negative 3/2 when you do common denominator and all that stuff. So now if you want to simplify this, and you should, the first derivative is going to be negative 3/2, and then you have square root of x cubed in denominator, and then minus 4. Slope of the tangent line is going to be the derivative computed at number 4, which is I said earlier, x equals 4. And now when you plug that, you get negative 3 over 2 square root of 4 cubed minus 4. Now you can either take the square root or do the cube first. Well, obviously you should take the root first and then cube it. So the whole thing is negative 3 over 16, because the square root of 4 is 2, 2 cubed is 8, and then times 2 in front is 16, minus 4, and the slope is negative 3 over 16 minus, and now I have to do 64 over 16 for the common denominator, and I get negative 67 over 16. Who picked these numbers? So now I have slope. Slope is negative 67 over 16. Y is the function computed at the point that we are looking at. So that would be at 4. So we have 3 over root 4 minus 4 times 4. So that's 3/2 minus 16. So y value is that's 32, so 29, negative 29 over 2. And here we have everything we need. Y equal mx plus b. This is notation for the original function, right? No prime. Right? Y is equal to f of x. Right. So y is negative 29 over 2 is equal to negative 67 over 16 times the x value plus b. These two guys cancel. We get a 4 there. So I have negative 29 over 2 plus 67 over 4 is b. And then finally b is equal to double this is going to be 57, right? So it's 10 over 4, which gives me 5 halves. So b equals to 5 halves. And now we have the tangent line. Y equals negative 67 over 16x plus 5 halves. And that would be the tangent line for this particular problem. Oh, no, it's just guys, you have to understand the difference between hard and annoying. This is extremely easy, but annoying because the fractions, right? But you can punch all of this in calculator, get those decimals and so on. The last part is the higher order derivatives. So what we did so far is the first derivative. You can also understand the function as the 0th derivative if you want to. You have the second and the third and the fourth and the fifth and the 105th derivative if you want to. So if I have a function, this is extremely short, 3x squared plus 5x minus 1, and I take the first derivative, well, that's 6x plus 5, right? I can take another derivative and get to the second derivative, which in this case would be 6. No, it doesn't make it more precise. It is the next layer, next derivative and next derivative. So you can see now that by the time you take the third derivative of the original function, you already got 0, and then any next derivative will be 0. Now, not all functions do this. Some functions are going to become larger. Some functions are going to stay the same. What's the 107th derivative of e to the x? E to the x, right? Because the first derivative is e to the x, and the second derivative is e to the x, and the third derivative is e to the x, right? So what is the third derivative? Third derivative is the first derivative of the second derivative. That's what it is. It's just you take the derivative one further, right? So you just keep going. That's all it is. So it's nothing special. If I ask for a third derivative, that's an annoying question because now you have to find the first derivative and then you have to find the second derivative so that you can finally find the third derivative. In application, we go to the third derivative and we don't go past that in applications. That's usually 3 derivatives.
What application would that be?
It will be the, let's say, kinematics of motion, right? You have the position function would be the original function. The first derivative is velocity, the second derivative is acceleration, and third velocity is jerk. So you go through those 3 iterations, and then there is nothing past that. So we'll deal more with this, but, you know.
What CPs do tomorrow?
Just the next 2 sections, I guess.
So 3, 4, and 5.
3, 4, 3, 5. We'll see if we can start 6 at least, so you can enjoy your weekend with more work, right? I know. That's the smile in it. I know. All right, guys. I'll see you tomorrow.